We've all been there, right? You ask a large language model to do something brilliant, write code, summarize dense article, compose a poem, and it delivers, totally nailing it. It feels like magic. But then you ask it a slightly different question, or perhaps one where it doesn't have all the facts, and suddenly it confidently presents something that's just plain wrong. It hallucinates. It's like watching a super genius confidently make up bedtime stories. It's baffling, and it's been a fundamental mystery plaguing our most advanced AI. Today, we're taking a deep dive into some groundbreaking research that finally explains why our AI companions can be brilliant one moment and totally make things up the next. This isn't just about understanding the problem. It's about finding a way to actually, prevent it.
And that's precisely the paradox this fascinating paper tackles head-on. It's titled Compression in LLMs, Bayesian in Expectation, Not in Realization, by Kalan, Karim, Kalan, and Awada. This isn't just another theory. It offers a unified framework that reconciles these seemingly contradictory behaviors. It proposes a way to understand why these models act Bayesian in expectation, not in realization. And crucially, it gives us powerful, quantifiable tools to predict and even prevent hallucinations, shifting them from unpredictable errors to something we can actually manage.
Exactly. Our mission today is to demystify that core paradox for you. We're going to peel back the layers on the underlying theory, what they call conditional Kolmogorov complexity, and the expectation level decompression law. Bit of a mouthful, but we'll break it down. Then we'll dive into the truly practical stuff, the operational tools like bits to trust, risk of hallucination, and the information sufficiency ratio. All of this is designed to help you not just understand why hallucinations happen, but how they can be effectively managed, turning a frustrating AI hiccup into a predictable, addressable challenge. So let's dig into this core paradox. On one hand, LLMs are phenomenal at in-context learning. You give them a few examples, and poof, they pick up a new task, almost as if they're performing a rapid form of Bayesian inference. They're constantly updating their internal beliefs based on the new data you provide, which is incredibly powerful. But then, here's the twist. They systematically mess up when the order of information shouldn't logically matter. We call this permutation and variance.
Right, think of permutation and variance like a bag of facts. If I tell you the sky is blue, grass is green, water is wet, the meaning stays the same no matter which order I say them in, right? A truly Bayesian system, one that really understands the underlying facts, wouldn't care about the order. It would always arrive at the same understanding of the world based on those facts. But LLMs often do care. Change the order of those facts even slightly, and you might get a different answer, or worse, a completely fabricated one. It's a clear mismatch with how a purely rational Bayesian system would operate, and yeah, it's been a real head-scratcher for researchers. What's fascinating here is that this discrepancy is exactly where the paper offers its core theoretical resolution. The key insight is that transformers, especially with their positional encodings, the bits that tell the model where each word is in a sequence, they aren't actually minimizing the absolute shortest way to describe something, regardless of order. That would be true permutation invariant Kolmogorov complexity, the ideal. Instead, what they're actually minimizing is the average shortest way to describe something across all possible orderings of the input.
Wait, hold on. So it's Bayesian on average, but not necessarily for the specific arrangement of facts I happen to feed it. That's a huge distinction.
Precisely. They're Bayesian in expectation, not in realization. That's the key phrase from the paper. They achieve excellent compression and calibration when you average their performance over many different possible orderings of an input sequence. But for any fixed input sequence you give them, the specific order does matter, and they can systematically deviate from what a truly order-agnostic system would produce. And this isn't just a hypothesis. The paper backs it up with the quantified martingale violation theorem, or QMV. This theorem provides an explicit mathematical bound for these order-induced deviations, showing they scale logarithmically with the sequence length.
Logarithmically. Okay, so as the input gets longer, the sensitivity to order does increase, but maybe not exponentially. It's more controlled.
Exactly. It means the more tokens an LLM has to process, the more sensitive it can become to the order of those tokens. But the sensitivity grows at a manageable, slower rate. It's that O-log n relationship. This positional processing, while essential for the model to understand the sequence and context of words like reading a sentence, it creates an inherent gap. A gap between its average case brilliance and its worst case potential for errors when the order isn't ideal. It's a feature, yes, but it also introduces this specific limitation.
Right, so we've peeled back the layers on why LLMs sometimes stumble due to this order sensitivity thing. But knowing the why is only half the battle, isn't it? For anyone actually using or building with these models, the real question is, how does this abstract idea of expected complexity actually explain why an LLM sometimes just makes
Yeah.
things up, hallucinates? Is it like it just gets overloaded and takes a best guess, even if they guess it's totally wrong?
That's a really good way to think about it, though it's perhaps more systematic than just a random guess. This is where the expectation level decompression law, or EDFL, that's theorem 3 in the paper, comes in. This law is absolutely critical because it quantifies precisely how much new information, let's call it delta bar, is needed to confidently shift from an initial belief, like a prior probability, maybe a guess, to a much stronger desired level of certainty, the posterior probability. Think of it like this. How many precise information bits, or NATs, as we call them in information theory, do you need to earn the right to confidently assert something?
So a NAT is just a unit of information, kind of like a bit, but using natural logarithms instead of base 2, used for continuous probabilities and stuff.
Exactly, you've got it. The critical takeaway for you, the listener, is that EDFL transforms hallucination from this seemingly random, unpredictable failure mode into a quantifiable consequence of information insufficiency. It means we can actually put a number on the information needed for a reliable output. For instance, the paper shows that for rare events where your initial guess, your prior probability Q is very low, like maybe less than 1% achieving a certain reliability, say PO1, like 95% confidence, requires a minimum information budget. If the model doesn't have that minimum information budget, it will lead to a compression failure, which often manifests as a hallucination. It's not random, it's a predictable information shortfall.
Okay, here's where it gets really interesting. Because if it's predictable, this isn't just a random error, it's a predictable information shortfall. That means we might actually be able to do something about it. I remember asking an LLM about my local coffee shop's hours, and it confidently gave me times for a place in a completely different city. Super frustrating. But this sounds like this framework, this EDFL thing, could have maybe flagged that answer as super risky before it even generated it. So what can we do? What are the practical tools?
That's where the real power of this research lies, absolutely. From the EDFL, the researchers derived 3 operational deployment tools. These enable practitioners, developers, or even savvy users to predict hallucination risk before text generation even begins, and then to manage that risk through what they call information budgeting. First is bits to trust, or B2T. This tells you the minimum amount of information, measured in NATs, that the model needs to gather or process to achieve a specific target reliability level you set, call it H. Then there's the risk of hallucination, or ρH. This is sort of the flip side. If you only have a certain amount of information available, your budget in, ρH tells you the maximum error rate, or risk you should expect. It quantifies the real-world risk. And finally, probably the most actionable one, is the Information Sufficiency Ratio, or ISR. This is a simple ratio calculated from the other two that dictates the model's answer or abstain decisions.
Answer or abstain. So it can decide not to answer if it's too risky.
Precisely. The ISR decision rule is incredibly straightforward. If the calculated ISR is less than 1, the model should abstain. It should say, I don't know, or ask for more information. If the ISR is 1 or greater, it has sufficient information relative to the required amount, B to T, and it can answer. And what's truly remarkable, I think, is that this threshold of 1.0 is analytically derived directly from the theory. It's not some magic number they found through trial and error. It falls right out of the math.
That threshold being analytically derived is huge, yeah. It means it's principled, not just tuned. Okay, to make these concepts super concrete for everyone listening, let's walk through that work example they provide in the paper. Let's say our target reliability is 95% confidence in the answer. So our acceptable error rate, H, is 0.05. First, let's look at the B2T calculation. How much info do we need? If we start with a very conservative initial belief, the paper uses an example where the prior chance, CLO, is only 2% or 0.02. The bits to trust needed, B2T is about 3.5 nats, quite a bit. But if we have a slightly less conservative initial belief, maybe a 10% prior chance, CLO, which will get 0.10, the BBT drops significantly to about 2 nats, 1.994. So you can see, right, the rarer an event or the more skeptical you are initially, the more information currency you need to spend to trust the answer. Okay, next, how does a given information budget translate to reliability? Let's flip it. Say our average initial belief is 10%, and we find the model has an information budget of 2.0 nats available for this specific query.
Using the formulas derived from EDFL, this budget translates to a maximum achievable success probability, Pmax, of about 95.1%. We've basically hit our 95% target confidence level. And finally, the crucial ISR gate decision. Let's use that same scenario. Prior is 10%, Q 0.10, required B2T was 1.994 nats, and our measured available information budget is 2.0 nats. The ISR is simply the ratio, B2T. So 2.0 divided by 1.994, which is just slightly over 1.0. Since ISR is 1, the rule says the model should confidently answer. But now, what if we were more cautious? What if we used that initial 2% prior belief? Keyword was 0.02. The required B2T was much higher, remember, 3.519 nats. With the same available information budget of E 2.0, our ISR would now be 2.0 divided by 3.519, which is about 1.57. In this case, ISR is less than 1. So the model should abstain, or maybe signal it needs more information. This provides a principled, data-driven way to manage that risk and stop confident-sounding nonsense. This theory sounds incredibly compelling, and okay, yeah, those tools seem powerful enough to make a real difference. But the big question always is, did the researchers actually test this out?
Does it work in the real world with actual messy LLMs? Or is it just, a beautiful theory on paper?
That's the crucial question, absolutely. And the answer is a resounding yes. The paper details 3 complementary experiments designed to rigorously validate the framework, and honestly, the results are incredibly encouraging. Experiment 1 focused on MDL optimality via permutation mixtures. They essentially tested if that O log n scaling for order sensitivity held up in practice. And they observed that how much the predictions varied when they shuffled the input order, what they called permutation-induced dispersion, it precisely followed that predictable logarithmic relationship, like a plus b log n. They even quantified it for specific models like Qwen27b and Llama 3.18b, finding different b values, showing architectural differences matter, but the log scaling holds. And crucially, they found that using permutation mixtures, basically shuffling the input facts a few times and averaging the model's predictions, consistently improved the ground truth likelihood and accuracy.
So shuffling the input a few times and taking an average is a simple, effective hack to make the model more reliable. That's clever, like getting a second, third, slightly different opinion from the same model.
Exactly. It helps smooth out the bumps caused by order sensitivity. And they measured these Jensen gaps, which were always positive. These gaps quantify the information penalty an LL pays for being order sensitive, basically, how much less efficient it is compared to a truly order agnostic ideal. Then came experiment 2, causal dose response analysis. This was, I think, a brilliantly designed randomized experiment. They varied the actual information content, like the number of relevant support chunks or facts given to the model, while carefully keeping the overall prompt length constant. This allowed them to establish a causal link. They found that hallucinations dropped by a consistent amount for every additional nat of relevant information provided. For Qwen27b, it was about 0.13 fewer hallucinations per nat, and for Llama 3.18b, about 0.11 fewer per nat. This directly validated the EDFL Theorem 3. It showed that giving the model more useful information causally reduces hallucination rates. It really hammers home that it's not just about prompt length, it's about the actual information content that determines hallucination risk.
That makes so much sense. More facts, less fiction.
Precisely. And finally, experiment 3 was a pre-registered audit for deployment calibration. This was the real-world test. They used a Gemma 29b model on new held-out question answering tasks and implemented that ISR 1.0 boundary for calibrated refusal. Just told the model, if ISR 1, don't answer. The results were quite stunning. They achieved 0% hallucination on the questions where the model did answer. It simply abstained when it calculated it couldn't meet the necessary information budget for the required reliability. They reported a very high boundary alignment, about 96.2%, for the ISR decision rule, with about a quarter of responses, 24.1%, being abstentions, so it wasn't afraid to say, I don't know. They even looked at practical trade-offs, finding that using just a few permutations, say M3, could capture most of the reliability benefits with less computational cost, only needing more shuffles, like M6, for really critical decisions. These experiments taken together provide really strong evidence that the theory holds up and the tools are genuinely effective in practice.
Wow, 0% hallucination by enabling refusal. That is incredibly powerful. And it sounds like this framework really shifts how we should think about trustworthiness in AI.
Absolutely. If we connect this to the bigger picture, this framework does a few key things. Firstly, it clarifies that positional processing, how LLMs handle input order, is this fundamental feature limitation trade-off. It's necessary for understanding sequences, but it inherently creates order sensitivity, scaling as O log n. Secondly, it convincingly argues that hallucinations are not random errors or some kind of mysterious AI ghost in the machine. They are predictable compression failures. They occur deterministically when the available information budget falls below the precise thresholds set by the EDFL. It demystifies them. And thirdly, and perhaps most profoundly, calibrated abstention, the ability for models to safely refuse to answer when unsure emerges naturally and predictably from these information theoretic principles. This provides a much more robust foundation for building reliable and trustworthy AI, moving beyond just detecting errors after the fact to actually preventing them from happening in the first place.
That's a total game changer. And okay, this isn't just academic theory. It has huge practical applications for you, the listener, whether you're just using LLMs daily or actually building systems with them. Imagine pre-generation risk assessment. You can use the ISR calculation to get a score, to know the hallucination risk before the LLM even starts typing its answer. That's huge. You could implement graduated responses based on different ISR thresholds. Like, if ISR is really low, maybe below 0.5, the model flat out refuses. If it's in a gray area, say 0.5 to 1.0, it might hedge its answer. Based on the information I have, it seems like X, but I'm not certain, signaling that uncertainty. And then if ISR is comfortably above 1.0, it answers confidently. This moves us towards much more nuanced and, frankly, more trustworthy AI interaction. Furthermore, it gives us a clear signal for information acquisition. If your system gets a low ISR score for a user query, you know precisely when to prompt the LLM to maybe search the web for more context or ask the user for clarification before attempting an answer. And for critical applications where reliability is paramount, using ensemble robustness through that permutation averaging technique seemed like a really practical step. The paper even mentions the future possibility of maybe developing a training time regularizer that could directly encourage models to have less prediction variance across different input permutations, complementing these inference time checks. Of course, the researchers are upfront about limitations too. The current work focuses mainly on binary yes-no or simple factual answers. Extending this to multi-class classification or generating complex, structured outputs is future work. And systematically investigating exactly how model scale and different architectural choices impact this positional bias is also an ongoing area. So, wrapping this up, what does this all mean for you? We started with that baffling paradox. LLMs can be brilliant, yet they confidently hallucinate. This deep dive has shown you the core reason. Our AI companions are Bayesian in expectation, not in realization. They're good on average across all possible input orders, but sensitive to the specific one you give them. That fundamental insight, combined with the expectation level decompression law, EDFL, and the practical tools like B2T, ROH, and especially the ISR1 threshold, it transforms hallucinations from these unpredictable failures into quantifiable, manageable risks. Hopefully, you now have a deeper understanding of why LLMs sometimes falter, and more importantly, a framework that provides real, predictive, and even preventive measures against hallucinations. It really points towards a future where we can be much more strategic, much more informed of how we use and, crucially, how we trust large language models, moving towards more reliable and transparent AI.
And this raises, I think, an important question for all of us to maybe ponder going forward. If we can now quantify the exact amount of information an LLM needs to avoid hallucination on a given task, how might this fundamentally change the way we design prompts, the way we curate training data, or even how we think about the ethical responsibilities of deploying AI in high-stakes situations? What are the deeper implications of building truly transparent AI systems that provably understand the limits of their own knowledge and can reliably tell us when they don't know enough to speak confidently? How will that change our relationship with AI?